Okay, welcome back. So we're going to do now a problem about basically a turbine that generates power, and what we need to find over here is what is the heat transfer between this control volume and the surrounding. Okay, but let's just read the problem statement. So steam enters, so we know the state over here of the substance will be steam, enters a turbine operating at steady state with mass flow rate of 4,600 kilograms per hour. So it's over here. So maybe one thing we can do right away. Okay, generally the units of time should be seconds, so this should be what? 1 hour is 3,600 seconds. So basically this will be equal to 4,600 divided by 3,600, which is about 1.2778 kilograms per second. All right. The turbine develops a power of 1,000 kilowatts. At the inlet, the pressure is 60, the temperature is 400, and the velocity is 10. At the exit, the pressure is 0.1 bar, the quality is 90%, okay, and the velocity is 30 meters per second. Calculate the heat transfer between the turbine and the surroundings. So basically what I need to find is Q over here. Alright, so this is not mandatory, but always good to show me that you understand the material. If you do the TV diagram, in this state, we work between the two pressures of 60 bars. Okay, we know it's steam. We can check later, but I'm pretty sure it's going to be somewhere over here, where you will know that P1 equals 60 bars. Okay, and a line over here, P2 equal to 0.1 bars. And we know this time we're going to be at 90%, so it's going to be somewhere over there. So if we do the figure of the process, it should be something like this. Okay, so now we know where to go and check for the tables. So let me zoom out a little bit. So here we need to go to the superheated tables. Here we need to go to the mixer tables, okay, to find those values. All right, so let's start the problem now. So basically what we have over here is, so on this figure again, this dashed line will be our control volume. So applying first principle of thermodynamics to control volume. What do we have? Heat transfer minus the work done by the control volume plus whatever mass is going in. So M H1, we can neglect the potential energy, plus V1 squared over 2 will be equal to what is leaving, M dot H2 plus V2 over 2. And the question over here is to solve for Q dot. So it will be equal to the power plus M H2 minus H1, and I can factor this out, plus 1/2 V2 squared minus V1 squared. So really, at this point, we are done with the problem. From now on, it's just a matter of make sure that when we go to the tables, we don't do any mistake. So on this equation over here, what do we know? We know that the power developed by the control volume is 1000 kilowatts. Okay, and on the previous page we had that it was equal to 1.2778. And now maybe let's do this one very quick, but we have to be careful for the units. Okay, so when we look at this term of 1/2 V2 squared minus V1 squared. Okay, remember the units for this. This is kilowatts, so we need to put this in kilowatts. So this is equal to what? The units for these ones are meter squared second square. So we need to transform that into what? Let's see. So we're gonna have 1 Newton equal to 1 kilograms meter second square. And then remember this is kilo, so we need to know that 1 kilojoules equal to 1000 Newton meters. So that will give us the kilojoules. Okay, and then okay. So you see that here we'll have what the newtons cancel the newtons, the meter square, this one will cancel, this one over here, this second square, this one we cancel with this one, and we are left with kilojoules. So when we multiply the kilojoules by, so we're left with kilojoules per kilogram. Okay, so now if we multiply this so let's do it in 2 steps. So this will give us units of kilojoules per kilogram. Okay, which is what we need so that they're consistent with the H. Alright, so now we need to find H1 and H2. So what do we know about H1? From the figure, we say that the state is superheated. So that means we need to go to, so for H1, we need to go to table, I think it's table H6, yes, table H6. And what do we know about that state? We know that the pressure is 60 bars, so at P1 equals 60 bars, and T1 equals 400 degrees Celsius. What do we have? So in the table A6, again, they give us the pressures in megapascals. But by now we know that then 60 bars would be 6 megapascals. Okay? So if we look at the table of 6 megapascals at 400, and we look at the H, we see that it's equal to 3178.3. So we can write H1 equal to 3178.3 kilojoules per kilogram. So you see the units will match once you get over here. Okay. Now we need to find H2. So for H2, we need to go to the table for the mixture. And we know that the quality over here is 90% or 0.9. Okay? So that's table A5 over here. But let's first here zoom out and let me change the page. Okay, so for H2, we said that we needed to go to table A5. So what do we know about the state 2? We know the pressure, which is at P2 equals 0.1 bar, which will be 10 megapascals. Okay, so if we go, so it will be, sorry, 10 kilopascals, because over here, let's see, they have the values in kilopascals. So if we go to 10, all right, what I need to find is the H. So we need to find here the H. So H fluid is 191.81. HFG is 2392.1. HG is 2583.9. The HFG is just the difference of this one minus this one. Okay? So from table F5, we're going to have that at 10 kilopascal, we have H fluid equal to 191.81. H gas equal to 2583.9. At the HFG, which is just the difference between both of them, is 2392.1. So once we know that, we know from the equation for the mixtures that then H2 will be equal to H fluid plus X2 HFG. Okay, so this is going to give us 191.81 plus 0.9 times 2392.1, which gives a value of H2 equal to 2343.91 kilojoules per kilogram. Okay, so I think we are almost ready. Let me go back for a second to this page just to make sure that we're not going to do the mistake. Remember over here we did all this for the units, but let's not forget that this value here we're going to have to divide it by 1,000 because of the 10 to the 3. Alright, so now let's go back over here and let's just say recalling the equation heat transfer equal to the work of the control volume plus the mass flow of H2 minus H1 plus 1/2 of V2 square minus V1 square. Alright, so this is going to give us what? we're gonna have 1000 plus 1.2778 factor of H2 2343.91 minus H1, which was equal to 3178.3 plus 1/2 of V2, which is equal to 30, and V1 is 10, so 30 squared minus 10 squared. But here, let us not forget that we need to divide by the 1000. Alright, so if we do this calculation, we get over here that this is equal to 1000 plus 1.2778 times minus 834.39 plus 0.4. So finally, at the end, we have that the heat transfer, that will be in kilowatts, is equal to minus 65.66. Okay, now the question here is, let me zoom out. So is this value correct or not? If you remember, for our sun convention, the work coming out of the system is positive, the work going in is negative. But for the heat, we have the other way around. The heat going inside the system is positive, and whatever is coming out here is negative. So the negative sign over here means that it's coming out. So that's the heat generated by the control volume, giving it to the surrounding. So it is as plotted over here. So as expected, the turbine is giving the 65.66 kilowatt of heat into the surrounding. So that will be it for this problem.